So, dear students, in today's lecture, we will discuss about the circuit elements, the basic circuit elements which are used to form an electric network. So, a detailed discussion about electrical networks, their types, will be discussed in forthcoming lectures. The purpose of today's class is to introduce you to some basic circuit elements. Okay, so these circuit elements, when connected together to one another in certain topology, whether all the circuit elements are connected in series with one another, or they are connected in parallel to one another, or they are connecting in a particular combination wherein we have series as well as parallel combination. So let us start with the lecture. The first thing which I would like you to know is that the electrical energy, basically it is convenient and efficient for production of light, mechanical energy and information processing. Um, so I just want you to give a glimpse of this electrical energy. What is an electrical energy and what are its uses, basically. So it is a convenient and efficient for production of light, mechanical energy and information processing. As you all know that in today's time we cannot expect our life convenience without electricity. Electricity plays a very important role in all of our lives, right? And we all know that almost all of our work, basically, or the tasks or jobs are done through electricity. So we make use of electricity, that whether we talk on phone, whether we use laptop or mobile, or we watch TV or anything, our fan, cooler, AC, our kitchen appliances, our laundry appliances, all they operate on electricity. So uh, electricity has become a very important utility of our life. Even the information processing, basically, okay, communication through mobile phone and all that, these are also based on electricity, right? You cannot expect communication without electricity. Okay, so we can also, so you can see, we can also transmit or transport the information over the tremendous distance by using electrical energy, right? And similarly, uh, we all know that the electricity energy does not, it is not available in natural form. We need to generate the electricity through certain means and methods. Okay, by using certain means and methods, we have to generate the electricity. We have thermal power plant, we have hydroelectric power plant, we have nuclear power plants, we have solar power plants. So we generate electricity. It is not available in natural way, in nature, right? So the next slide is about a little bit of physics associated with electricity, electrical energy. So you all have gone through all these points in your school in physics class, I hope. So uh, the fundamental electric charge carrying particles are electrons. We know electrons are negatively charged particles, and then we have protons also, which are positively charged particles, right? They all possess charge, and the unit of charge is coulomb, right? The unit of charge is coulomb, right? So we all know that the electronic charge is basically equal to 1.62 into 10 raised to power 19 coulomb, and it is negative for electron and positive for proton, right? Then, because we know that coulomb is a larger unit, and so we have some smaller units to express the charge capacity. So we use micro coulomb, basically. Okay, and we also have studied the Coulomb's law. Okay, so we don't have to go in deep in all these concepts. It is just a brief introduction of that physics which is associated with electricity. Okay, so the force, basically, which is the force here is between the two charges Q1 and Q2 is given by this formula, wherein Q1 and Q2 are the charges in coulomb, and then d is the distance between these two charges. So let us say there is a positive charge and then there is a let us say either it could be a positive charge or it could be a negative charge, right? So it can be a positive charge or it can be a negative charge. So the distance between these two charges is, let us say, d. Okay, and the force and the q1 is this one charge and q2 is this one charge, and the force between these two is given by this particular formula, right? And then epsilon is basically the basically the permittivity, right? Okay, then let us understand what is potential difference. This also you have studied in your physics. So a potential difference can be defined as it is the work done when a unit positive charge is moved from a point B in the field to another point A. So the work done in bringing a charge from one point to another point. Okay, so that is termed as the potential difference, right? And the unit of potential difference is volts, and 1 volt is equal to 1 joule per unit positive charge. It means this much of work is done in bringing a unit positive charge from a point B to a point A. So if you are bringing a unit positive charge from a point B to point A, so the amount of work done that is done is basically termed as potential difference. So symbol of potential difference, which is also known as voltage, is given by either small v or capital V, right? So now, if the work must be done, on the charge, energy input to the charge, as it moves from point B to A, the voltage of A is higher than that of B. That is, voltage rises from B to A and is indicated as VAB. Now, what does it mean? It means how do we indicate the voltage? So as we are saying that we are, let us, there is a point A and then there is a point B. Okay, so we are moving a charge from this point B to a point A. Okay, and the work is done to move this charge from point B to A, and we are calling it as potential difference, right? So um, the voltage is basically increases from B to A, right? When the charge is moving from B to A, so the voltage is assumed to be increasing from B to A. If it is moving from A to B, let us say the charge is moving from A to B, so in that case, the voltage is increasing from A to B, or it is decreasing from B to A. Vice versa is also true. Means you can mention it in two ways. One is either the voltage is increasing from B to A, or the voltage is decreasing from A to B. So that voltage is VAB. That voltage is VAB, right? So here you can say it is VAB. VAB means B to A. The voltage is from B to A. So this is the direction of the voltage. So voltage is directed from B to A, right? Similarly, if it is from A to B, so we will write VBA. So that means it is from B to A, right? No, sorry, A to B. The voltage is from A to B. So the direction of voltage is from A to B, right? So this is how we mark the direction of the voltage. And we also know for the if the reference frame is same, so in the same reference frame, we can say that VBA is the voltage from A to B is equal to VAB, is equal to VAB, right? But negative of that. That means the magnitude will remain same. However, the direction would be different, right? So it is also mentioned here. You can read there are two ways of indicating the voltage difference on as it is shown in the diagram. So here, let us say you have two diagrams, this one and this one. So in this one, you can say the direction of the arrow is given as from towards A. Basically, the tail is shown towards B and arrow is shown towards A, right? So it is VAB. Okay, it is VAB, right? So because the voltage is from B to A, this is one way of showing it. This is one way of showing the direction of voltage. Similarly, we can also show the voltage as this one. So whichever point is at higher potential, that point is termed, it can be shown as positive, and whichever point is at lower potential, so that can be indicated as negative. That can be indicated as negative, right? Okay. So there are two ways of representing the voltage direction. One is this one, and another one is this one. Either you can indicate it through polarities plus and minus, or you can indicate it through an arrow. So whenever you say, for example, there is a network, there is a, let us say, there are two terminals. There are two terminals, A and B. So this is A, let us say this is B, and the direction of voltage is shown like this. So it means the voltage is from B to A. So we will write VAB. So this is at lower potential B, and A will be at higher potential. So this is one way, and the second way is that you will mention the higher potential, you'll mention as positive, and the lower potential you will mention as negative, right? So this is how the potential difference or voltage difference or voltage is represented. Then we have electric current. You all are aware of what is an electric current. What is an electric current? I is equal to dq by dt, rate of change of charge. Okay. So when the charge flows, electric current produces. And charge which we are talking about is the electron basically. When electron flows, why electron flows? It flows because of the potential difference. So it is a potential difference, so which is responsible for the flow of electron. Okay, because of this pressure difference created between two terminals, 2 points, the electron would flow. And when electron flow, we have an electric current also. So electric current, we all know that when electron flows in one direction, let us say this is the direction of electron flow, so the conventional current will flow opposite to this particular direction, mean the opposite to the direction of flow of electron, right? So now the positive direction of the current is the direction in which positive charge flows. This direction is opposite to that of an electron flow. So if the electron flows in this direction, so the current will flow in this particular direction, right? The unit of electric current is ampere, right? And 1 ampere is 1 coulomb per 1 second. So 1 coulomb of charge is flowing per second. So this gives you 1 ampere of current. And the symbol that is used for electric current is either small I or it is capital I. For static values, we make use of capital L, letter of current, and for time varying current, for instantaneous value of current, we make use of small letter I. So do not confuse with I here with iota. Iota or is also used, I is also used as under root -1 in mathematics in complex number theory. So do not get confused with this iota or this I with under root -1. In electrical systems, we do not make use of iota as under root -1. No, we do not make use of it. We make use of J, in fact, J operator, which is used as under root -1, because I is also used for electric current. So to avoid any kind of confusion, for complex number, for imaginary number, J is basically used as a imaginary operator, right? The symbol of charge is Q, and so this is all about the electric current here. So you can say that the current from these two diagrams, okay, if current is flowing from A to B, so it is taken as positive, and if the current is flowing from B to A, it is taken as a negative current. So there is no negative and positive direction as such. Okay, here the positive direction and negative direction is mentioned with respect to flow of electron. If the, as I mentioned earlier also, that if electron flows in one direction, the current will flow in the opposite direction, right? But let us not talk about the flow of electron, let us talk about the flow of current. So there is no positive or negative direction for electric current. It is always with reference to something. Okay, if I say that my current is some current, I current is flowing in this particular direction, let us say A to B, right? So if I take this current as positive current, it is up to me. I am taking this current as positive current. So if I see that some current will flow, if some current is flowing from B to A, if some current is flowing from B to A, so that current I will take as negative, and this current is negative with reference to this particular current. Okay, this current is negative because I have taken a direction positive already. For example, if there is a point, if there is a point, let us say there is a point. Let us say there is a point, right? So if there are two branches coming out of this particular point, so in one branch there is a current coming towards this particular point, and in another branch the current is going out of this point, and the current here is, let us say, I1, and the current here is, let us say, I2. There are two currents, I1 and I2. So which one you will take as positive, which one you will take as negative? There is no set rules for this. There is no thumb rule for this. You can say that I1 is positive because it is outgoing current, or you can say that I2 is positive because it is incoming current. If you are taking I2 as positive, and because it is incoming current, so by default I1 will become negative. I1 will become negative. So it is negative with respect to the direction of I2, and there is no set rule or thumb rule for the direction of current, which one is positive and which one is negative. Okay, now let us come to next slide. So again the current is continued here. How to represent the direction of current? Let us say there are 2 points A and B. If the current is flowing from A to B, so I will write I A B. So it is A to B. It is like this. It is A to B. The current is A to B. Sorry, current is flowing from A to B. And if the current is flowing from B to A, so I will write IBA. So it is from B to A. Unlike voltage representation, in voltage representation, how do we represent? If I am writing VAB, what does it mean? The voltage is from B to A. But if I am writing IAB for current, the current is from A to B, like this. Okay, current is flowing from A to B, it is like this. Okay, so this is the representation. So because you need to know, whenever you will find this kind of notation or notations basically in the numerical or study material, so it would become easy for you to understand. If IAB is written, so it means there is a current I which is flowing from some point A to B. If VAB is written, that means there is a voltage V which is appearing across B and A point, and the direction is from B to A. Direction is from B to A, right? Okay. Now, the electric current basically is categorized in two categories. One is the unidirectional, and second one is the alternating current. Unidirectional current is also known as DC current. So it is a, like you can see in the diagram here, right? You can see in the diagram here. So you can see that the current is, this is unidirectional current. Unidirectional current, it is having one direction only. So it could be either positive direction or it could be either negative direction. So you can also have a negative, like minus I here. So in the fourth quadrant basically, right? Like this. Okay. So it could be positive or negative, but it will have only one direction. And this is the nature of direct current basically. So this is what we call as direct current. The example are cell, battery, solar cell, etc. Okay, so these all are the examples, right? Similarly, you have an alternating current here. So in alternating current, you can see it is a bidirectional current. It is a bidirectional current. So it is having positive magnitude as well as negative magnitude, right? So it is changing its direction across our reference line. And what is the reference line here? The reference line is this time axis. So the magnitude of current is basically varying across this time axis, right? So it is positive as well as negative. So generally our electricity which we receive at home, or which is basically generated at either any of the plant, hydropower plant or thermal power plant or nuclear power plant. Okay, all these, the nature of electricity which is generated here is alternating. Okay, so electricity is alternating, bidirectional signal is generated, bidirectional voltage as well as bidirectional current, right? So the example is your power systems basically. Okay, so power systems, fine. Alternator, what is an alternator? Alternator is the combination two words, and these two words are alternating generator, means AC generator. AC generator, right? So now, so there are two types of current, two categories of current, DC as well as AC. Similarly, you have a voltage also, DC voltage and AC voltage, right? Then let us come to the circuit elements, because an electric circuit basically comprises of certain elements, certain components which are connected to one another in a certain topology. Okay, so any element basically can be represented like this. Okay, so generally we have uh, uh, 3 to 4 types of circuit elements. Like we have voltage, we may have current source, we have resistor, we may have capacitor, we may have inductor, right? So then below three, resistor, capacitor, inductor, these are the passive elements. These are the passive element, and above two, these are the active elements. Okay, so an electric circuit is basically made up of all these elements, right? Voltage, current, resistor, capacitor, inductor, like that. Okay, so okay, now you can see here in this particular diagram, you can see current is basically shown here, and a voltage is also shown, and then you have a plus and minus. Now what does it indicate? It indicates that across an element, voltage appears. Voltage appears across an element. Okay, and current flows through an element. Current flows through, voltage appears, right? Okay, you may have let us say you may have an AC source, right? And there may be a terminal, there may be two terminals, these terminals are open, let us say. So no current will flow here in these terminal. Okay, no current, because these two terminals are open, right? But you will have a voltage, you will have a voltage across these two terminals, because voltage always appear across the element or component, and current always flows through the element or the component, right? It has voltage and electric current associated with it. Okay, means this is how you will represent the current and voltage um, as far as a component is concerned. Okay, you all must have noticed or studied or seen that whenever you have to measure current, you always use an ammeter, and you connect that ammeter in series with any component. Let us say there is a resistance, okay, and you connect ammeter in series with this. Now why do we connect in series with this? Okay, that also we will study what is the reason behind it. Okay, okay, because we know that current is flowing through this resistance, it is not appearing across the resistance. Current is not appearing across the resistance, but when you have to measure the voltage across this resistance, what you will do, you will connect a voltmeter like this. V means you will connect a voltmeter in parallel to the resistor, because we know that the voltage is appearing across this particular resistor. Voltage is appearing, right? Okay, so this is written here, voltage is an across variable. It is an across variable because it appears across the element, and current is a through variable because it flows through the component, right? Voltage is the cause and current is its effect. Now, there are certain the circuit elements which we are talking about are categorized as, like, we have active elements, we have no, passive elements, right? Okay, and then okay, we have active elements, we have passive elements. Now, what are active elements? Active elements are those elements which are capable of generating the electricity. Okay, which are capable of driving an electric circuit, an electrical system, like your cell. It is capable of driving a torch, your mobile phone, your toy, your any. appliance which operates on battery cells, right? Okay, and your alternator, AC generator, power systems, right? They are capable of generating electricity, right? And because of that electricity, we make use of our electrical appliances. Only then electrical appliances will operate. So active elements are those elements which can generate energy, electricity, or electrical energy, right? So we have battery generators, then operational amplifier. This you will study when you will, in your basic electronics also, diodes and all that. Why do we call them active elements, right? Okay, so as far as here electrical systems are concerned, we have batteries, we have generators, or we have DC generators, AC generators, right? Okay, so we also call active elements as electrical sources. Okay, active elements are also known as electrical sources. And then we have passive circuit elements. So passive circuit elements are basically those elements which do not generate electricity, but they are used in electrical circuits in some way, because to have the analysis of electrical circuit, we make use of all these passive elements, right? So they do not have their electrical energy, they do not generate electrical energy, rather they consume electrical energy. A resistance dissipates electrical energy in form of heat. A capacitor stores electrical energy in form of electrostatic field charge. We all know a capacitor stores charge. Inductor, okay, so inductor, what it does, it stores electrical energy in form of magnetic energy, right? So they do not generate electricity, rather they either dissipate electrical energy or they store electrical energy, and that is why we call them as passive elements, right? So these are the schematic representation. A resistance symbol is represented like this, capacitor is represented with two parallel lines, and an inductor is represented as a coil, right? So we all know what is a resistor, what is an inductor, what is a capacitor, what is a resistance, what is capacitance, what is inductance. You all are well aware of that, right? Okay, all these are linear, kind of linear elements, and yeah, inductor and capacitor, they show a little bit of non-linearity also, right? Okay, so a resistor opposes the flow of electric current through it. Okay, and we know for any linear circuit, Ohm's law is applicable. You all know what is Ohm's law. V is equal to IR, right? Okay, under the constant physical conditions, temperature, pressure, the voltage across a conductor is always proportional to, directly proportional to the current flowing through it. Okay, and where V is proportional to I, and we can say V is equal to IR. So IR here is a constant value which represents the resistance of the conductor, right? Okay, fine. So similarly, you have inductor which stores the energy in the form of electromagnetic field. Then capacitor stores energy in form of electrostatic field, right? Okay, so the detailed analysis of these three would be studied in forthcoming lectures. As of now, we only have to understand what are the various types of circuit elements. So first category of circuit elements is active elements and passive elements. Active elements are those elements which store which generate electrical energy, and passive elements are those elements which do not generate electrical energy, rather they either dissipate electrical energy or they store electrical energy in some form. Let us come to, okay, so this was all about today's lecture, today's class, my dear students. So the purpose was to understand the types of electrical circuit elements, right? Thank you so much.